This is the second part of our discussion on fast extraction of isosurfaces. We are going to talk today about a second range search method that efficiently looks at all the cells and identifies cells that contain the isosurface. The algorithm that we are going to see is by Signoni et al. This is an algorithm that uses a data structure called the interval tree. The algorithm proceeds as follows. Remember that the range search methods attempt to store the collection of ranges as intervals in such a way that it supports efficient identification of the isosurface cells. Signoni et al. Proposed the following method. They first sort all the data points based on the min and max values. So remember that the data points are our cells from the grid. So let's say there are n cells. We have 2n endpoints of the corresponding intervals. The first step sorts all of these endpoints, x1 through x2n. Let the midpoint be called delta. So naturally the midpoint of the median is going to be x sub n. The interval tree considers all these intervals. There are n intervals, remember. So the interval tree uses the midpoint to partition the intervals into three sets: I sub delta, I sub left, and I sub right. I sub delta contains all the intervals that contain delta. So these are the intervals where the min and max are respectively less than and greater than delta. I sub left consists of all the cells whose max is less than delta. Similarly, I sub right consists of the collection of cells whose min is greater than delta. So this naturally leads to a hierarchical subdivision of the collection of intervals. The only difference with the earlier subdivisions is that the intervals are stored at every node in this tree, whereas in our earlier subdivisions, the intervals were actually stored at the leaves of the tree. The interior nodes were essentially hierarchically partitioning either the domain or the range. In this interval tree, we will end up storing the intervals at possibly every node in the tree. Signoni et al. Showed that the interval tree can be used to identify the isosurface cells in much faster time compared to the earlier approaches. Let's look at how this interval tree works. To help us understand how the interval tree works, let's use the example that I showed earlier to motivate the fact that it is difficult to partition the collection of intervals. So here is a collection of intervals, and on the top I show the real line. So there is a global maximum and a global minimum. We have, let's say, n intervals. Let's name their endpoints x sub i's and sort them. So the sorted order is going to look like this: x1, x2, x3. There is going to be an x4. It looks like two of the endpoints are exactly the same. For now, let's assume that they are different. There is an x5 above and an x6 here, followed by an x7, the min for the interval here, x8, and so on until you have x2n. Right. So we have 2n endpoints, and we have ordered them in increasing order, and we have now chosen the midpoint. Well, this is not really the midpoint, right? We would like to choose one of the endpoints of the interval as the midpoint. So this was the earlier mean that was chosen as the partition for the subdivision, whereas now we would like to use something else. We would like to use x sub n as the midpoint. So let's say this point here is x sub n. So I would like to choose the value corresponding to that. So this is x sub n, right? So this is the median. And now what I want to do is to identify what is stored at this root node, I sub delta, right? So I sub delta consists of all the intervals that contain x sub n. So let's try and show them in green. So this interval, and then you have another interval here, 2, you have a third interval here, and then you have a fourth interval. These are the 4 intervals that belong to I sub delta. Now, tree do, it partitions the other intervals into I sub left and I sub right. The collection of intervals that belong to I sub left will come from this collection, and I sub right similarly to the right of x sub n, right? So between I sub delta, I sub left, and I sub right, we have all the intervals, right? So the partition proceeds hierarchically or recursively. So similarly, I sub left is partitioned into 3, one corresponding to the partitioning element that we find at possibly corresponding to one of the endpoints, and so on. So this is how we hierarchically subdivide the intervals. One question that you may want to ask yourself is, what is the time taken to construct the tree? So the time for construction. So to answer this question, of course, you need to answer another related question, which is when do you stop the recursion? That's easy to answer. That is when there are no intervals associated with a node. Then you stop the recursion. So this is a question for you. What is the time for constructing this interval tree? For this marching cubes algorithm, we are interested more in the query time. What is the time required to identify the collection of all intervals that contain a particular ISO value, let's say C. So how does that proceed? This is also quite easy now, but let's write it down nevertheless. So if my ISO value C is equal to the median, so as in when I check the ISO value with the median at the root, if it is equal, then I know that I have to traverse through all intervals in I sub delta and report them. If C is less than x sub n, then I know that I have to traverse the left subtree. Now in addition, there may be some intervals in I sub delta that may contain my ISO value. So I have to traverse through this collection of intervals as well. Now if C is greater than x sub n, similarly we have to traverse, let's try and write that here just to finish. If C is greater than x sub n, then similarly I have to look at I sub right and I delta. So that's the outline of the query algorithm. So the recursion hopefully is clear. We will let's postpone the discussion on how to process I sub delta, but hopefully the recursion is clear. If C is less than x sub n, then I look at the left subtree. Similarly, if C is greater than x sub n, I look at the right subtree. Let's look at this procedure again. So what do we have? If C equals x sub n, I said that I need to look at I sub delta. So essentially I have to report all the intervals in I sub delta. So there is nothing to be done here. So after we report all the intervals in I sub delta, we exit. So we are essentially done. Just to illustrate, let's look at one of the cases if C is less than x sub n. So naturally there is the recursion I sub left. The question is, how do I process I sub delta? In this case, to report all intervals that contain C. Let's remember how I sub delta was created. So remember that spanned X sub n, long or small, they all spanned X sub n. And I know now that C somewhere here, that is C. So it is less than X sub n. How do I quickly report the intervals from I sub delta, the green intervals? How do I quickly report those intervals that contain C? This is the question. So note that all the max for these intervals are greater than C. So there is no point looking at the max. This will not give us any information. The max for all these intervals, the max here for all these intervals are definitely going to be greater than C because they are greater than X sub n. So clearly we want to look at the min values to report the isosurface cells. So the way I sub delta is stored is by storing all these intervals in the form of two arrays. One array is sorted based on the min values and the other is sorted based on the max values. The min values are sorted, this is increasing order, and the max you want to sort in decreasing order. This should become clear now. So in order to identify which intervals from I sub delta contain C, I go through the min array. Note that it is sorted in increasing order of the min values. I read off the min values one by one. So let's see, this is the first one. Let me switch. Right. So this is the first one, first interval, and then the second one. But when I hit the third, I already see that the min value is greater than C. So I stop my traversal. So I essentially continue traversing the min array until I hit a value which is greater than C, and I report all these intervals as isosurface cells. So this is how I process I sub delta. Processing I sub left is essentially just a recursion. Similarly, when so in the case of C greater than X sub n, I would process the right subtree recursively, and then I would process I sub delta. At this time, I would look at the max array, which is now sorted in decreasing order of the max values. And again, I will read off all the max values until I reach a max value which is less than C. Right? So what is the runtime for this query? Let's look at this. Recursion, but note that this recursion is a very simple recursion. I either go to the left subtree or to the right subtree. So I essentially traverse a path from the root towards one of the leaves. So this path has to be of size log n, because what we have here is a balanced tree, given that we are using the median. So we have a log n due to the path traversal, that's the recursion. The time taken to process I sub delta in both these cases is exactly equal to the number of isosurface cells. Remember that we have pre-sorted the arrays, the two arrays based on the min and max values, and we read only as many elements from the array as the number of isosurface cells that come from I sub delta. So if I add up all the contribution of all these array reads, I get a factor k. So my total runtime is O of log n plus k. So that's the algorithm using the interval tree by Signoni et al. So when I compare this with the num required O of under root n plus k. So clearly Signoni et al. Is doing better, and in fact they are doing the best possible. So the algorithm by Signoni et al. Is actually worst case optimal, so that we denote that it is theta of log n plus k, because you cannot hope to do better than log n, and of course you cannot hope to do, if you remember, compared to the domain search algorithm, we are much better. So the domain search required k log n. So in fact, some of these endpoints coincide with each other. So if h is the number of unique endpoints, then we actually have a runtime which is O of log h plus k. Here h is the number of unique endpoints. So this could be a better analysis compared to log n plus k, if we recognize that the endpoints could be integers, and in that case there are only finitely many possible endpoints, so h could be much less than n. So we saw an optimal range search method. So this was optimal in terms of the runtime performance, even in terms of the space requirement. So the space that was required by this algorithm was O of n, right? In fact, it needed 2n. So recall that each interval was stored twice, one in increasing order of min and once in the decreasing order of max. So the space requirement is 2n. While this does not look too bad in the worst case, note that n can be quite high, and this 2n is additional space that you need. So additional in the sense that you need to store your data, and just to support the isosurface extraction, you need an additional 2n space. So in fact, this is one of the drawbacks of the range search method. So while they are fast, and they are faster than the matching cubes algorithm in general, and specifically the domain search methods, the range search methods need this additional memory. So in the next part of this discussion, we are going to look at another approach to extract isosurfaces, namely contour propagation.